In this video, we describe Lewis dot structures, and we apply the rules to draw a couple of simple molecules like methane and molecular oxygen. Lewis dot structures is the most rudimentary type of covalent bonding model, and it's a very useful model in that it allows you to see how electrons are shared between atoms to form covalent bonds in molecules. And when coupled with the VS-EPR theory, it's a really powerful tool to describe the structures of a variety of simple molecules. Now, something interesting about Lewis dot structures is that that model was derived before we actually had a quantum mechanical description of the atom. So it's interesting to know that even though we're handling electrons in Lewis dot structures, those concepts emerged before we actually knew that electrons could be described by orbitals and concepts like that. All right, so let's get started here with the rules for Lewis dot structures. And what I'm going to do is try to apply those rules to a couple of molecules like CH4, methane, and then molecular oxygen, O2. Right. The first rule that guides the description of Lewis dot structures is that you need to count the number of valence electrons in the entire molecule. Okay, so you come to methane and then see what is the electronic configuration of carbon, and that is helium 2s2 2p2. That means that carbon contributes with 4 valence electrons. Then you have hydrogen, which is a 1s1 electronic configuration. That means that you have 1 valence electron. So the total number of valence electrons that you have in the molecule for the case of methane is 8. Okay, so that's 8 valence electrons. Now for oxygen, the electronic configuration is helium and then 2s2 2p4. Okay, so each oxygen atom contributes with 6 valence electrons. Okay, and that means that you're going to have a total of 12 valence electrons in that O2 molecule. All right, so being able to determine the number of valence electrons quickly by simply looking at the periodic table is something that you're going to have to do if you want to succeed drawing Lewis dot structures. Okay, the second rule, or the second piece of guidance here, is that you have to identify whether there is a central atom and then draw it at the center of the structure. Okay, so for methane, it seems to be pretty obvious. Okay, we have determined that methane has 8 valence electrons. Right, so you would draw, determine if there's a central atom, which in the case of methane is carbon, and then just draw it at the center of the molecule, and then draw the rest of the atoms in the periphery of that central atom. Okay, so that is relatively easy to do for methane. In molecular oxygen, we're not going to have a central atom, so we cannot do that, but we can still place the oxygen atoms nearby. Okay, so that is the second rule, or the second piece of guidance, again, that says that try to identify where the central atom is. Okay, the next rule would be draw bonds between the terminal atoms and the central atom. Okay, so in the case of methane, we actually have that the hydrogen atoms are terminal, and then the carbon atom is central. Well, the first thing that you have to do is connect these atoms with a bond. Okay, now that bond actually requires 2 electrons. Okay, so to make these 4 bonds, these 4 connections between the central and terminal atoms, we actually need a total of 8 of the electrons that we have. Okay, notice that in the case of methane, we actually have 8 valence electrons that we can utilize to build the structure. Okay, so there's actually no electrons left over in the case of carbon after we actually draw the terminal bond, the bond between the terminal atom and the central atom. All right, let's take a look at oxygen. Here we draw a bond between the 2 terminal atoms. In this case, there's no central atom. So notice that while here we actually have 0 electrons left after we draw the bonds, here we only employ 2 electrons to draw this bond, which means that the total number of electrons that we have left over would be 10 electrons. Okay, so that is the third rule. And then the fourth rule would be if there's any electrons left over after drawing these initial single bonds between terminal and central atom, then you have to place them in the molecule so that each atom sees an octet unless it's hydrogen, which only needs to see a duet of electrons. Okay? And then something useful is that when you place these electrons, these leftover electrons around the molecule, you have to start with the terminal atoms first. Okay, so in the case of methane, there's actually no electrons left over, so there's nothing to do here. However, we need to see if every atom is surrounded by 8 electrons, unless it's hydrogen, where you only need 2 electrons. Okay, we'll look at the central atom, and we see that this carbon atom sees 2, 4, 6, and 8 electrons. So actually, you can see that this carbon atom is surrounded by an octet of electrons, and that is exactly what needs to happen. Now, for hydrogen, you don't need an octet, you need a duet. Okay, so 2 electrons, and you see that each hydrogen atom is nearby to 2 electrons. So in principle, we're actually done with the Lewis structure of methane, which will be simply this. Okay, this satisfies all the rules, and is actually the actual true structure of methane. Now, for oxygen, again, the fourth rule is that you take the electrons left over, and then you place them in atoms using the terminal atoms first, and then try to see if you can reach an octet for each one of the atoms involved. Okay, so let's try to place those 10 electrons that we have left over in the terminal atoms. There's no central atoms, so that's not a distinction. And we can start perhaps with this. And the way to place it is as pairs, okay, around the atoms. Okay, so here I have 1, 2, 3 pairs around the oxygen, and I'm putting 3 pairs because that gives me an octet for this atom, right? I would have 2 electrons, 4, 6, and then 2 of this one. That would be an octet. And that means that I have 10 minus 6, I have still 4 electrons left over that I can put here around this oxygen. All right, so that will be my initial attempt. After this drawing, I don't have any electrons left over. Now the question is whether the atoms in my structure satisfy an octet. And what I see is that this atom has 2, 4, 6, 8. Okay, so it does see an octet, but in this case, the atom on the left, we have 2, 4, 6. That is actually 2 electrons shy of an octet. All right, so the question is, what is it that we can do? How can we redraw the structure in order that both atoms see an octet? But so an idea here is that if these 2 electrons are actually not forming a lone pair, as we have right here, but instead I take those 2 electrons and I make a bond between the atoms with them, okay, the resulting structure now is going to have an octet for both atoms, right? So notice how now this oxygen sees 8 electrons, 2, 4, so 4 electrons in lone pairs, and then 2, 4 electrons in that double bond, that is 8 electrons for the oxygen atom on the right, and that will be exactly the same as the atom on the left. Okay, so that structure satisfies the octet for both, and I have exactly the same electrons that the sum of the valence electrons of the atoms involved. Okay, so in this video we have seen the rules for drawing Lewis-Dot structures, and then we have applied them to a couple of simple molecules. In next videos we're going to continue to do a few examples of Lewis-Dot structures, and then we'll incorporate a little bit more of challenge in those structures.